Hello, dear friend, and welcome to the Bedtime Lab, where tonight we're embarking on a gentle journey through the stars. We're going to explore nuclear fusion, that wondrous process that powers the very stars twinkling above us. So, settle in, get comfortable, and let your imagination drift among the cosmos. And while you're here, feel free to share where you're watching from. It's always nice to know where in the world we're finding new friends. Did you know that nuclear fusion is like the heart of a star? It's where tiny particles come together in an incredible dance, creating energy that lights up our universe. Imagine hydrogen atoms, the simplest and most abundant elements in the cosmos, merging together under immense pressure and temperature. These atoms combine to form helium, and in the process, they release a staggering amount of energy. It's like a cosmic handshake that powers the light we see when we gaze at the night sky. Here's a fascinating fact. The core of a star is unimaginably hot. We're talking about temperatures reaching 15 million degrees Celsius. Can you imagine such heat? It's hard to comprehend here on Earth, where the hottest we get is a mere fraction of that. And yet, in the heart of a star, it's just another day at the office. Speaking of heat, did you know that the energy produced by nuclear fusion in a star's core can take thousands, sometimes even millions of years to reach the surface? It's true, this energy travels slowly through the dense layers, bouncing around like a pinball in a game before it finally emerges as the starlight that illuminates our night sky. It's a patient journey, almost like the star is slowly exhaling its light. Let's think about the sun for a moment, our nearest star. It's a giant ball of nuclear fusion happening right above us. Every second, the sun fuses around 600 million tons of hydrogen into helium. That's more mass than all the cars on Earth combined. And yet, the sun will keep burning for another 5 billion years or so. It's like an endurance runner with a seemingly endless reserve of energy. Here's something interesting to consider. Stars come in many different sizes, and their mass influences how they perform fusion. The more massive a star, the hotter and more intense the fusion process. Giant stars can be 10 times the mass of our Sun or more, and their cores can reach temperatures much hotter than smaller stars. These massive stars burn through their fuel more quickly, living fast and dying young in the grand scheme of cosmic time. Do you know what happens when a massive star runs out of fuel? It results in one of the universe's most spectacular events, a supernova. This is an explosive end, where the outer layers of the star are blown away in a brilliant display of light and energy. A supernova can outshine an entire galaxy for a short time, leaving behind a beautiful, expanding cloud of gas and dust. And speaking of endings, not all stars meet such a dramatic fate. Our Sun, for example, will have a much quieter end. It will eventually swell into a red giant before shedding its outer layers, leaving behind a glowing core called a white dwarf. These remnants can shine for billions of years, like a cosmic nightlight. Now, let's touch on something truly mind-bending. The heaviest elements in the universe are forged in the hearts of stars during fusion. Elements like carbon, oxygen, and even iron are created within these celestial furnaces. It's fascinating to think that the atoms in your body, the very building blocks of life, were once part of a star. We are, quite literally, made of stardust. As we continue this journey of discovery, imagine the vastness of the universe. There are around 100 billion stars in our galaxy alone, each one a glowing beacon of nuclear fusion. Some stars are so distant that their light takes millions of years to reach us. When you look up at the stars, you're seeing them as they were long ago, a glimpse into the universe's past. And here's a thought to drift off to. The light from stars we see now may have traveled vast distances across the universe just to reach us. It's like a cosmic message in a bottle, filled with stories from the distant past. Every star has its own tale, its own journey through time and space. So, as you close your eyes and drift into a peaceful sleep, remember that you are part of this incredible cosmos, connected to the stars in ways both profound and beautiful. Let the wonder of nuclear fusion and the mysteries of the universe fill your dreams, dear friend. Until next time, sleep well under the watchful gaze of the stars. Let me share something quite remarkable about the sun. Despite its enormous size and the incredible energy it outputs, only a tiny fraction of its power reaches Earth. In fact, we receive just over 1/1000th of the sun's total energy. Yet, even this minuscule amount is enough to warm our planet, drive weather systems, and support life. Isn't it amazing how even a little bit of starlight can have such a profound impact on our world? Now, consider this. The sun's core, where nuclear fusion occurs, is not a solid or even a liquid. It's a state of matter known as plasma, which is like a superheated gas where electrons have separated from their atoms. Plasma is often called the fourth state of matter, and it's fascinating to think that at such high temperatures, even atoms cannot stay intact. This state allows the fusion process to occur as the atomic nuclei are free to collide and merge. Have you ever wondered what keeps stars from collapsing under their own gravity? It's a delicate balance between the outward pressure generated by nuclear fusion and the inward pull of gravity. This balance is known as hydrostatic equilibrium. When a star is in this stable state, it can continue shining for millions to billions of years. It's like a cosmic tug-of-war that maintains the star's structure and life. Here's a thought-provoking fact. In the early universe, hydrogen and helium were the only elements formed during the Big Bang. All other elements were created later inside stars through nuclear fusion. This means that the universe had to wait for the first stars to form and go through their life cycles before heavier elements could exist. Imagine a universe where stars had to act as cosmic forges to build the complexity we see today. Speaking of elements, did you know that different types of stars produce different elements? Smaller stars, like our Sun, primarily convert hydrogen into helium, but more massive stars can go beyond this, fusing helium into carbon, oxygen, and even heavier elements like silicon and iron. The more massive the star, the more complex the fusion processes it can support before it reaches the end of its life. And here's something wondrous. When a massive star goes supernova, it disperses the elements it has created throughout space. These elements then become part of new stars, planets, and even living organisms. Think of it as a cosmic recycling program, where the materials from old stars become the foundation for new celestial bodies. It's incredible to realize that everything we see around us has been through this cycle many times over the eons. Can you imagine how bright some of these massive stars must be? Stars that are several times the mass of our Sun are not only larger, but also much more luminous. Some of these stars, known as blue supergiants, are so bright that they shine thousands of times more intensely than the Sun. It's almost as if they're determined to leave a lasting impression on the cosmos before their inevitable demise. Let's ponder this. The Sun produces more energy every second than humanity has used in its entire history. This staggering amount of energy is a testament to the sheer power of nuclear fusion. If we could harness even a fraction of this energy sustainably, it could revolutionize our energy systems here on Earth. The potential for such a breakthrough is a dream for scientists working on fusion technology. It might surprise you to learn that stars are born in regions of space known as stellar nurseries or nebulae. These vast clouds of gas and dust are the perfect environment for stars to form. As regions within the nebula collapse under gravity, they become hot and dense enough to ignite nuclear fusion. It's a beautiful thought that stars, which appear so distant and unchanging, have such humble and dynamic beginnings. Did you know that the largest stars can end their lives as black holes? After a supernova, if the remaining core is massive enough, its gravity can cause it to collapse to a point of infinite density. This creates a black hole, an object so dense that not even light can escape its grasp. It's both terrifying and fascinating to think of these cosmic giants transforming into such enigmatic and powerful remnants. Here's another captivating fact. The color of a star tells us a lot about its temperature. Blue stars are hotter and more massive, while red stars are cooler and often smaller. Our sun, with its yellowish hue, sits comfortably between these extremes. This color-temperature relationship is a simple yet profound insight into the nature of stars, allowing astronomers to estimate their properties even from afar. And finally, let's marvel at the sheer variety of star systems within our galaxy. Some stars, like our Sun, are solitary. Others are part of binary systems, where two stars orbit each other. There are even systems with multiple stars, where the gravitational dance becomes even more intricate. Each system is unique, offering a glimpse into the diverse ways in which stars can exist and interact in the universe. As you let these thoughts gently settle in your mind, consider the vastness of our universe, filled with stars of all kinds. Each one is a testament to the unimaginable processes of nuclear fusion, shaping the cosmos in ways both subtle and grand. Allow yourself to drift into a peaceful slumber, wrapped in the comforting knowledge that you too are made of stardust, a part of this wondrous and infinite spectacle. Sweet dreams as the stars keep watch over your night. Have you ever contemplated how stars manage to stay so perfectly spherical? It's the result of gravity pulling equally from all directions toward the center of a star, giving it that iconic round shape. This uniform pull ensures that the nuclear fusion happening within their cores is evenly distributed, allowing stars to shine steadily and brightly. This reminds me of a fascinating fact. The energy produced by nuclear fusion in the Sun's core can take thousands, even up to 1 million years, to reach the surface and radiate into space. Imagine energy taking such a leisurely journey through the layers of a star before it finally reaches us as sunlight. And speaking of journeys, did you know that stars can travel astonishing distances through space? They are not just stationary points of light, but are constantly moving, albeit slowly from our perspective. This movement is part of the dynamic dance of our galaxy, with stars orbiting the galactic center. Over millions of years, this motion can lead stars to new neighborhoods in the galaxy, a reminder of the ever-changing nature of the cosmos. Here's a mind-boggling thought. Some stars have such strong magnetic fields that they are billions of times more powerful than Earth's. These magnetic fields can influence the star's surroundings, creating spectacular phenomena like sunspots and solar flares. It's incredible to think about the immense forces at play within stars, silently affecting their environments on such a grand scale. Have you ever wondered about the sizes of stars? While some stars can be hundreds of times larger than our Sun, others are much smaller, sometimes just a fraction of its size. These smaller stars, known as red dwarfs, are the most common type of star in the universe. Despite their diminutive size, they can burn steadily for trillions of years due to their efficient nuclear fusion processes. It's a humbling reminder of how diverse and varied stars can be. Interestingly, the fusion process within stars is incredibly efficient. For example, in the Sun, only a small fraction of its mass is converted into energy, yet this is enough to power the entire solar system. Just a tiny percentage of the Sun's mass is lost to fusion every year, yet this loss provides all the energy that sustains life on Earth. The efficiency of this process is truly awe-inspiring. Here's something that might surprise you. The very existence of planets, including Earth, is owed to the nuclear fusion processes of stars. During the late stages of a star's life, it can expel its outer layers into space, enriching the surrounding areas with heavy elements that were created through fusion. These elements then become the building blocks for planets and other celestial bodies. It's remarkable to think that every atom in our bodies was once part of a star long ago. Speaking of stellar contributions, did you know that the presence of elements like carbon, nitrogen, and oxygen in our atmosphere is largely because of past supernovae? These colossal explosions spread the elements forged in stars across the cosmos, eventually becoming part of planets like ours. Without these massive stellar events, life as we know it would not be possible. It's a testament to the essential role stars play in the cosmic ecosystem. Now, consider this. While stars are born in clusters, not all of them remain close to their siblings. Over time, gravitational interactions can lead to stars being flung out of their birthplaces, setting off on solitary journeys through the galaxy. Some of these rogue stars can travel at incredible speeds propelled by the gravitational forces of massive objects. The idea of stars wandering the galaxy alone is both poetic and intriguing. In the grand cosmic scheme, stars not only create elements, but also serve as markers of time. By studying stars, astronomers can learn about the history and evolution of our universe. For example, by examining the light from distant stars, scientists can deduce their ages and the conditions of the early universe. Stars are like time capsules, holding clues to the past and helping us understand the origins of everything we see around us. Here's a thought to ponder. While stars like the Sun have a seemingly stable lifespan, they will eventually exhaust their fuel. When that happens, stars will undergo dramatic changes. Our Sun will expand into a red giant, consuming the inner planets before shedding its outer layers and leaving behind a dense core known as a white dwarf. This transformation is an inevitable part of a star's life cycle, a poignant reminder of the impermanence of all things. Interestingly, not all stars meet the same fate. Some can end their lives in spectacular supernova explosions, while others may quietly fade away. The final stages of a star's life are determined by its initial mass, with larger stars having more explosive and dramatic endings. It's a captivating aspect of stellar evolution that each star follows its unique path, shaped by the forces of nuclear fusion and gravity. Lastly, consider the long-lasting impact of stars on their surroundings. Even after a star has ceased to exist, its influence can persist for millennia. The remnants of supernovae, for example, can form nebulae that become the birthplaces of new stars. This cycle of birth, life, and death is a continuous process that has been shaping our universe for billions of years. It's a comforting thought that even in the vastness of space, there is a sense of continuity and renewal. As you let these facts settle into your thoughts, imagine the night sky filled with stars, each one a beacon of light and life, gently illuminating the darkness and whispering stories of cosmic wonders. Have you ever stopped to think about how stars like our Sun are essentially enormous nuclear reactors suspended in the vastness of space? The process that powers these stellar giants is known as nuclear fusion, a truly remarkable phenomenon. Fusion occurs at the heart of a star, where the temperatures soar to millions of degrees. It's in this incredibly hot core that hydrogen atoms collide and fuse together under immense pressure, forming helium and releasing vast amounts of energy. This is what keeps stars shining brightly for billions of years. Interestingly, the fusion process is not just a simple transformation of hydrogen to helium. There are several pathways that fusion can take, depending on the star's mass and its stage in the life cycle. For stars the size of our Sun, the predominant process is called the proton-proton chain reaction. This chain reaction consists of a series of nuclear reactions that ultimately convert hydrogen into helium, all the while liberating energy that escapes as light and heat. Did you know that the sheer pressure at the center of a star is what enables nuclear fusion to occur? The gravitational pull of a star's mass compresses its core to such an extent that atoms are forced together, overcoming their natural repulsion. It's this incredible pressure that allows stars to sustain fusion reactions, producing the energy that we see as starlight. Here's a fascinating thought. The energy released from nuclear fusion in stars is the result of a tiny amount of mass being converted directly into energy. This is described by Einstein's famous equation, E equals mc squared, where E represents energy, m is mass, and c is the speed of light. This equation demonstrates how even a small amount of mass can be transformed into a tremendous amount of energy, which is exactly what fuels the stars. Speaking of energy, did you know that the light from our Sun takes about 8 minutes to reach Earth? This journey begins deep within the solar core, where the energy generated by fusion takes thousands of years to travel to the Sun's surface before it can finally escape into space as sunlight. It's a staggering timescale, highlighting the complex inner workings of our closest star. And here's an intriguing fact. Stars can fuse elements heavier than helium during their lifetimes. As a star exhausts its hydrogen supply, it begins to fuse helium into heavier elements like carbon and oxygen. This process, known as stellar nucleosynthesis, is the cosmic forge that creates the building blocks of life. In more massive stars, fusion can continue to produce even heavier elements, up to iron, in their cores. Have you ever wondered why fusion stops at iron in the cores of massive stars? It's because fusing elements heavier than iron requires more energy than it releases. Once a star reaches this stage, it can no longer sustain itself through fusion alone, leading to dramatic changes that can culminate in a supernova explosion. This explosive end scatters the star's enriched materials across the cosmos, seeding future generations of stars and planets. Here's something captivating. The rate of nuclear fusion in a star is finely balanced with the force of gravity. This balance is known as hydrostatic equilibrium and is crucial for a star's stability. If the rate of fusion decreases, gravity causes the star to contract, which increases pressure and temperature, thereby boosting fusion. Conversely, if fusion rates increase, the star expands, reducing pressure and temperature to stabilize the process. Now, consider this. Not all fusion reactions produce light. Some generate neutrinos, tiny subatomic particles that pass through matter almost undisturbed. Trillions of neutrinos are streaming through your body this very second, born from the fusion processes in the Sun. These elusive particles are crucial for understanding the inner workings of stars, providing insights into nuclear reactions that we can't observe directly. Speaking of the Sun, its core fuses about 600 million tons of hydrogen into helium every second. Despite this immense scale, the Sun has enough hydrogen to continue fusing for several billion more years. It's a testament to the vast reservoirs of fuel that stars possess, allowing them to shine steadily across cosmic timescales. Here's a thought-provoking fact. The Sun loses mass as it fuses hydrogen into helium. This mass loss, though tiny relative to the Sun's total mass, results in a slight reduction in the Sun's gravitational pull over time. It's a subtle effect, yet it has implications for the orbits of planets and other bodies in the solar system. And did you know that the energy generated by nuclear fusion in stars is what powers the universe? From the light that warms our planet to the distant galaxies visible through telescopes, the energy from fusion is the driving force behind the brilliance of the cosmos. Without it, the universe would be a cold, dark, and lifeless place. Finally, consider the role of fusion in the life cycle of a star. As stars fuse hydrogen into helium and other elements, they change in size, temperature, and brightness. These changes are part of a star's natural evolution, with fusion dictating its journey from birth to eventual death. It is a process that connects every star in the universe, weaving a common thread through the tapestry of the cosmos. As you reflect on these insights, feel the gentle glow of the stars, each a testament to the powerful forces at work in the universe, guiding you into a serene slumber. As we drift deeper into the wonders of starry skies, let me share a surprising revelation with you. Stars are not born with the ability to fuse elements heavier than hydrogen. It is only when they evolve and reach higher temperatures and pressures that they can create elements like helium, carbon, and oxygen through fusion within their cores. This evolutionary process is akin to a star unlocking new levels of potential as it ages, a cosmic coming of age, if you will. Here's another curious fact. The core of a massive star can reach temperatures exceeding 100 million degrees Celsius. At these extreme temperatures, the fusion of helium into carbon becomes possible, a process that requires far more energy than the fusion of hydrogen into helium. Such intense conditions are a testament to the incredible power contained within these celestial giants. Imagine this. The fusion processes in stars are responsible for creating nearly all the elements found in the universe. From the carbon in your body to the oxygen you breathe, these elements were forged in the fiery hearts of stars, then dispersed across the cosmos by supernovae and other stellar events. It's a humbling thought that the very matter that makes up our world was once part of a distant star. Speaking of distant stars, did you ever ponder the lifespan of stars based on their mass? Massive stars, those much larger than our Sun, burn through their fuel at a prodigious rate, living fast and dying young in a cosmic sense. These stars can live for only a few million years before ending in spectacular supernova explosions. In contrast, smaller stars like red dwarfs burn their fuel slowly, granting them lifespans that can extend to over 100 billion years. Now, picture a star cluster, where stars are born from the same cloud of gas and dust. Despite being siblings, the stars in a cluster can have dramatically different fates depending on their initial masses. While some become red giants and ultimately supernovae, others, much like our Sun, will quietly expand into red giants before shedding their outer layers to become white dwarfs. It's a stellar family dynamic defined by the intricate dance of nuclear fusion. And here's a fascinating insight. The energy output of a star is not constant throughout its life. As it exhausts its nuclear fuel, a star's luminosity and temperature change, leading it through different stages of its life cycle. This journey is marked by transitions into various types of stars, such as red giants and white dwarfs, each stage reflecting the ongoing fusion processes within. Imagine the sheer power of a supernova, an explosion so bright that it can outshine entire galaxies for a brief time. This explosive event marks the end of a massive star's life, scattering newly forged elements into space. These elements become part of the interstellar medium, the raw material for new stars, planets, and even life. It's as if stars are the universe's ultimate recyclers, perpetuating the cycle of creation and destruction. Consider this intriguing fact. Some of the heaviest elements in the universe, like gold and uranium, are thought to be formed during the cataclysmic events of neutron star collisions. These collisions occur when the remnants of supernova explosions, in the form of dense neutron stars, collide and merge. The resulting fusion processes produce an incredible burst of energy and create elements that are then spread throughout the universe, reflecting further on the life cycle of stars. Did you know that as a star ages, its outer layers can expand and cool, transforming it into a red giant? During this phase, the star's outer layers are puffed up, sometimes even engulfing nearby planets. For our Sun, this transformation will occur in about 5 billion years, potentially including the orbits of Mercury and Venus in its vast, fiery embrace. And here's something that might intrigue you. White dwarfs, the remnants of stars like our Sun, are incredibly dense. A single teaspoon of white dwarf material would weigh several tons on Earth. These stellar remnants shine faintly as they slowly cool over billions of years, a final, dim echo of the nuclear fusion that once powered them. Imagine the peacefulness of a star settling into the quietude of a white dwarf stage, having spent its fuel and completed its cosmic journey. These stars no longer undergo fusion, but instead emit stored thermal energy as they gradually fade into the dark void of space. Finally, let me share a thought about the eventual fate of all stars. As they exhaust their nuclear fuel and end their cycles through various transformations, they contribute to the ever-changing tapestry of the cosmos. Whether through the gentle fading of a white dwarf or the explosive finale of a supernova, stars are the keystones of cosmic evolution, each playing a role in the ongoing story of the universe. As you contemplate these celestial wonders, embrace the tranquility of the universe's rhythm and let the whispered stories of stardust guide you gently into restful dreams. Have you ever wondered how stars keep their radiance for millions or even billions of years? It turns out that nuclear fusion is the secret to their enduring brilliance. In the heart of a star, hydrogen atoms are squeezed and fused together to form helium, releasing vast amounts of energy in the process. This energy radiates outward, lighting up the night sky. But here's a curious twist. The very process that fuels stars also creates a delicate balance. The incredible pressure from fusion reactions pushing outward is countered by the immense gravitational pull trying to collapse the star inward. This cosmic tug-of-war keeps the star stable for much of its life. Now, think about how stars are born. They emerge from enormous clouds of gas and dust, known as nebulae. Within these clouds, regions of higher density can collapse under their gravity, triggering the birth of a new star. As the cloud contracts, the temperature and pressure increase until nuclear fusion ignites in the core. This marks the beginning of a star's life, a journey driven by the powerful forces of fusion. What's truly astonishing is the range of elements stars can create. As stars evolve, they can forge elements heavier than hydrogen and helium through a process known as nucleosynthesis. Elements like carbon, nitrogen, and oxygen are synthesized in the stellar furnaces, enriching the universe with the building blocks of life. It's as if stars are cosmic alchemists, transmuting simple elements into a rich variety of atoms that make up everything we see around us. Did you know that the heaviest naturally occurring elements are not formed in stars like our Sun, but during the explosive demise of massive stars? In supernova explosions, the intense heat and pressure enable the production of elements such as iron, gold, and uranium. These dramatic events scatter these elements across the cosmos, seeding future generations of stars and planets. It's a stunning example of how destruction leads to creation in the universe. Here's a lesser-known fact. Star fusion can vary based on the star's size and composition. In a star like our Sun, the fusion process primarily converts hydrogen into helium. However, in more massive stars, the fusion process can extend further, forming a chain reaction known as the CNO cycle, which involves carbon, nitrogen, and oxygen as catalysts. This cycle is particularly significant in stars more massive than our Sun, highlighting the diverse methods stars use to sustain their glow. Imagine for a moment the size of these stellar powerhouses. The most massive stars, known as hypergiants, can have diameters over 1,000 times greater than our Sun. With their immense cores, they can reach temperatures and pressures far beyond those of smaller stars, allowing fusion processes to occur at astonishing rates. These stars, though short-lived in astronomical terms, contribute vastly to the chemical enrichment of the universe through their eventual explosive deaths. Stars also have fascinating periods known as variable phases, where their brightness changes over time. This can occur due to changes in the fusion processes or external factors like the presence of a companion star. Some stars pulsate with regular periods, growing brighter and dimmer as they expand and contract. These stellar oscillations can provide insights into the internal structure of stars, much like seismic waves reveal the interior of Earth. Speaking of companions, binary star systems are particularly intriguing. In such systems, two stars orbit a common center of mass. The proximity of these stars can lead to intriguing interactions, such as mass transfer, where material from one star can be pulled onto the other. This can dramatically affect the fusion processes within the stars, sometimes leading to explosive phenomena like novae, or even altering the star's evolutionary paths. It's also captivating to consider how stars are classified. The Hertzsprung-Russell diagram is a tool astronomers use to categorize stars based on their luminosity and temperature. This diagram reveals a star's evolutionary stage and helps predict its future. For instance, stars on the main sequence, where our Sun resides, are in the prime of their fusion-driven lives. As they age, they move off this sequence, transforming into red giants or white dwarfs. And here's an intriguing thought. Some stars can end their lives as neutron stars or black holes. After a supernova, if the remaining core is between 1.5 to 3 solar masses, it can collapse into a neutron star, an incredibly dense object composed mostly of neutrons. If the core is more massive, it may continue collapsing to form a black hole, an enigmatic region where gravity is so strong that not even light can escape. These endpoints are the result of the incredible powers unleashed by nuclear fusion and subsequent gravitational collapse. As you ponder these facts, let the mysteries of nuclear fusion and stellar evolution fill your mind with wonder. Stars, with their fusion-fueled lives, are the architects of the universe, constantly transforming and creating. Each twinkle in the night sky is a testament to the timeless dance of nuclear reactions, a cosmic ballet that continues to shape the universe as we know it. As you drift into slumber, may the gentle glow of these distant giants guide your dreams, reminding you of the vastness and beauty of the cosmos. Now, imagine the different pathways stars can take depending on their mass. Did you know that stars significantly more massive than our Sun can undergo a process called photodisintegration during their final stages? This occurs when the core temperature becomes so incredibly high that gamma rays actually break apart iron nuclei, leading to the star's collapse. It's a dramatic sequence of events that underscores the immense energy involved in stellar life cycles. Here's something fascinating. Neutron stars, which are born from the remnants of massive stars, can spin at incredibly rapid rates. These stellar remnants, which can be as small as a city but contain more mass than our entire Sun, can spin several hundred times per second. This rapid rotation is a relic of the conservation of angular momentum from the original star, resulting in a unique celestial lighthouse effect when they emit beams of radiation. Speaking of stellar remnants, let's consider white dwarfs. These are the final evolutionary state of stars like our Sun. What's surprising is that despite their small size, roughly that of Earth, they are incredibly dense, with a pinhead's worth of white dwarf material weighing as much as a car. This density is due to electron degeneracy pressure, the force that supports the star against further collapse. Transitioning from stellar deaths to stellar births, did you know that the Sun, in its youth, was not alone? Our star likely formed in a cluster with thousands of other stars, all born from the same molecular cloud. Over time, gravitational interactions scattered these siblings throughout the galaxy, leaving the Sun as a solitary traveler in the vast cosmic expanse. Let me share another intriguing fact. Stars can rejuvenate themselves under certain conditions. This happens in binary systems where a red giant transfers mass to a white dwarf companion, potentially igniting helium fusion and causing the white dwarf to shine anew. This transformation can give the appearance of a star returning to a younger state. Have you ever wondered about the fate of helium in a star? After hydrogen is exhausted, helium becomes the next fuel for fusion, forming carbon and oxygen in a process known as the triple alpha process. This occurs at much higher temperatures and pressures than hydrogen fusion, illustrating the escalating energy demands of stars as they age. Here's a surprising twist. Not all stars end their lives explosively. Some, particularly low-mass stars, simply puff away their outer layers to form beautiful planetary nebulae before settling quietly as white dwarfs. This gentle fade contrasts sharply with the violent supernovae experienced by more massive stars. And speaking of stellar explosions, consider the phenomenon of gamma-ray bursts. These are among the most energetic events in the universe, thought to be associated with the collapse of massive stars or the merging of neutron stars. For a few brief moments, they can outshine entire galaxies, releasing as much energy in seconds as our Sun will emit over its entire lifetime. Did you know that a star's metallicity, or the abundance of elements heavier than helium, can significantly influence its evolution and fusion processes? Stars with higher metallicity tend to lose mass more rapidly, affecting their size and temperature. This characteristic can lead to different pathways in their life cycles, highlighting the diversity of stellar evolution. Here's a curious fact about our own Sun. It's not an ordinary star, but rather a relatively rare type known as a G-type main sequence star. These stars, often referred to as yellow dwarfs, make up only a small fraction of the stars in our galaxy. Most stars are actually smaller, cooler, and redder, belonging to a class known as red dwarfs. Imagine the sheer number of stars in our galaxy alone, estimated to be between 100 to 400 billion. Each one of these stellar bodies is a complex fusion reactor, continuously transforming light elements into heavier ones. This ongoing nuclear alchemy plays a crucial role in the chemical evolution of the galaxy, enriching the interstellar medium with the raw materials for new star formation. Speaking of galaxy-scale processes, consider this. The Milky Way itself is moving through space at an incredible speed, pulled by the gravitational forces of surrounding galaxies. Within this dynamic environment, star formation is an ongoing process, with about 7 new stars forming each year. This continual cycle of birth and death maintains the galaxy's vibrant stellar population. And here's an unexpected thought. The Sun's fusion-generated energy is not produced instantaneously. Photons created in the core take over 100,000 years to reach the Sun's surface due to the dense plasma environment. It's as if the light from our own star is a message from the distant past, journeying through the Sun's layers before finally illuminating our world. As you let these facts settle in your mind, consider the vast network of stars that populates our universe. Each one is a testament to the enduring power and mystery of nuclear fusion, an intricate dance of particles that shapes everything from galaxies to the atoms in your body. As you drift into dreams, let the thought of these cosmic wonders fill your imagination, guiding you through the starry tapestry of the night sky. Let me tell you about a fascinating aspect of nuclear fusion in stars. The process is immensely sensitive to the temperature and pressure conditions within a star's core. Did you know that even a small increase in temperature can dramatically accelerate the fusion rate? This sensitivity ensures that stars are incredibly self-regulating. If the fusion process heats up, the core expands slightly, cooling down and slowing the reaction, an exquisite balance that keeps stars stable for billions of years. Speaking of balance, consider this intriguing fact. The pressure in a star's core reaches staggering levels due to the immense gravitational forces at play. For instance, in the Sun, the pressure at the core is equivalent to about 200 billion times that of Earth's atmospheric pressure. It's this extreme pressure that allows nuclear fusion to occur, as hydrogen nuclei overcome their natural repulsion to fuse and form helium. Here's a surprising thought about the Sun's energy production. It converts approximately 400 million tons of hydrogen into helium every second. This fusion process transforms a small fraction of that mass directly into energy, as described by Einstein's famous equation E equals mc squared. Despite the Sun's massive energy output, this rate of fusion allows it to shine steadily for billions of years without significant changes in size or luminosity. Have you ever wondered why stars don't just explode immediately given their internal conditions? It's due to the delicate balance between gravitational forces pulling inward and the outward pressure from nuclear fusion. This equilibrium explains why a star can remain stable for so long, burning steadily and predictably until its fuel is depleted. Speaking of fuel, did you realize that the heavier elements produced in the core, like carbon and oxygen, form the vital building blocks for planets and life? These elements are synthesized through successive stages of fusion in massive stars, eventually being cast into space through stellar winds or supernovae, seeding the cosmos with the ingredients for future star systems and, ultimately, life itself. Here's an intriguing perspective. The fusion process in stars creates neutrinos, ghostly particles that barely interact with matter and can pass through entire planets without a trace. Billions of these neutrinos pass through your body every second, a silent testament to the nuclear reactions continuously occurring in the stars above us. Have you ever considered the sheer energy involved in stellar fusion? The energy generated by fusion in the Sun each second is equivalent to the detonation of millions of nuclear bombs. Despite this vast energy release, the vast distances of space ensure that we receive just the right amount of warmth and light necessary for life to thrive on Earth. Switching gears, it's worth noting that not all stars follow the same fusion pathways. Depending on their initial mass, stars can take different routes in their fusion processes. For example, very massive stars can undergo carbon fusion, a reaction that our Sun will never achieve. This diversity in stellar fusion leads to a fascinating variety of end states and celestial phenomena. Here's a curious fact. When a star exhausts its hydrogen fuel, it doesn't mean the end of nuclear fusion. Instead, the core contracts and heats up, igniting helium fusion in a more intense and energetic phase of the star's life. This phase leads to the formation of heavier elements and often results in dramatic changes in the star's size and luminosity. Reflect for a moment on this. The Sun's core, where fusion occurs, is incredibly dense, with its material packed tightly together at around 150 times the density of water. This core is a seething cauldron of plasma where fusion reactions churn tirelessly, sustaining the Sun's brilliance. Here's something to ponder. The vast majority of stars end their fusion lives as white dwarfs, but a select few, those with extremely high mass, can undergo further fusion stages until iron is formed. Iron marks the end of the road for fusion, as it requires more energy to fuse than it releases. This leads to the catastrophic collapse and eventual explosion of these stars as supernovae. And speaking of supernovae, these spectacular explosions scatter elements across the cosmos, contributing to the creation of new stars and planets. The very atoms in your body are likely forged in such stellar forges, highlighting the deep connection between your existence and the life cycles of stars. Consider this final thought. As stars evolve and change, they often experience dramatic shifts in their internal structures and fusion processes. These changes can influence a star's brightness and color, offering astronomers valuable clues about their age and composition. Observing these variations allows us to piece together the intricate life stories of stars, a cosmic narrative written in the language of nuclear fusion. As we conclude this exploration of fusion, let these insights into the star's inner workings drift gently into your thoughts, like whispers from the universe itself. Each fact is a step in understanding the remarkable processes that light our skies and shape our world. May these stories of fusion guide you into a realm of dreams where the stars continue to shine in their eternal dance. Did you know that the fusion process isn't exclusive only to the most massive stars? Even smaller stars, like red dwarfs, engage in nuclear fusion, though at a much slower pace than our Sun. In fact, these diminutive stars burn their fuel so efficiently that they can outlast larger stars by trillions of years. Imagine a star with a lifespan stretching over 1 trillion years. It's a remarkable testament to cosmic endurance. As we dive deeper, consider the role of temperature in fusion. The core temperature of a star needs to reach millions of degrees for fusion to commence. For instance, our Sun has a core temperature of approximately 15 million degrees Celsius. This intense heat is crucial for overcoming the electrostatic forces that keep atomic nuclei apart allowing them to collide and fuse. And here's another thought. While hydrogen fusion is the most common process in stars, helium fusion can create carbon through the triple alpha process. This complex chain reaction involves the fusion of 3 helium nuclei, known as alpha particles, into a single carbon nucleus. This is a vital step in the production of heavier elements within stars. Speaking of which, it's intriguing that the energy output from fusion helps maintain the star's structure. The outward pressure from energy production balances the inward pull of gravity, preventing the star from collapsing under its own weight. Without this balance, stars would simply crumble. Have you ever wondered why fusion doesn't happen naturally here on Earth? It's because the conditions necessary for nuclear fusion, extreme pressure and temperature, are nearly impossible to reproduce at such a scale on our planet. Even in laboratories where scientists attempt to initiate fusion, replicating the conditions of a stellar core remains a formidable challenge. And consider this. Each second, the Sun loses about 4 million tons of mass, transformed directly into energy. This staggering energy release is what powers our entire solar system, yet it's a tiny fraction of the Sun's overall mass. Over its lifetime, the Sun will lose only a small percentage of its total mass to fusion. Here's something that might surprise you. Stars like our Sun will eventually expand into red giants, engulfing nearby planets, including potentially Earth. During this phase, the outer layers of the star swell dramatically while the core continues fusing helium into heavier elements. The transformation into a red giant is a spectacular example of how a star's life evolves over billions of years. In contrast, speaking of different stellar fates, some stars might end their lives as neutron stars. These incredibly dense remnants result from the supernova explosions of massive stars, with matter so tightly packed that a sugar cube-sized piece would weigh as much as a mountain. Have you considered how fusion contributes to the star's color and brightness? Stars burn at different temperatures, and these variations are reflected in their color. Hotter stars appear blue or white, while cooler stars appear red or orange. The color of a star can reveal a lot about its temperature and the stage of fusion it's currently in. Meanwhile, the brightness of a star is often a direct result of the fusion process occurring in its core. The more massive the star, the more intense the fusion reactions, leading to greater luminosity. Another fascinating point is that heavier stars can undergo multiple stages of fusion beyond just hydrogen and helium. In these stars, fusion continues until the core is composed of iron, the most stable element in nuclear reactions. Iron, interestingly, signals the end stage for fusion in stars. Beyond this point, fusion would consume more energy than it produces, triggering the eventual collapse of the star. Such a collapse often ends in a dramatic supernova explosion, dispersing elements into the cosmos and enriching future star systems with the building blocks of planets and life. Speaking of future stars, did you know that the remnants of supernovae can serve as the nurseries for new stars? The shock waves from these explosions compress surrounding gas and dust, initiating the gravitational collapse that can lead to star formation. This cycle of star birth and death, fueled by fusion, plays a crucial role in the evolution of galaxies. Moreover, the fusion processes not only create elements, but also contribute to the electromagnetic fields that shape interstellar environments. These fields influence the movement of charged particles, affecting how matter is distributed and stars are born. Reflecting on the intimate connection between fusion and life, it's humbling to realize that the calcium in your bones, the oxygen you breathe, and the iron in your blood were all forged in the hearts of long-gone stars. This cosmic alchemy is a gentle reminder of our place in the universe, linking us to the stars in a profound and elemental way. As stars continue their fusion-driven cycles, they whisper the secrets of the cosmos, creating a tapestry of light and energy that we can observe and ponder even from our small corner of the universe. Each night, as we gaze at the sky, we're not just seeing stars, we're witnessing the ongoing story of fusion, a dance of creation and transformation that connects us to the very fabric of existence. Let me share something interesting with you. The fusion processes within stars are responsible for some of the most intense phenomena in the universe. For instance, did you know that when a massive star reaches the end of its fusion cycle, it can result in a hypernova? Hypernovae are even more powerful than typical supernovae, releasing energy equivalent to billions of times the energy our sun will emit over its entire lifespan. Such events can generate gamma-ray bursts, the most energetic form of light known to humanity, detectable across vast cosmic distances. Here's another fascinating tidbit. While stars like our sun primarily fuse hydrogen into helium, more massive stars can fuse elements all the way up to iron over their lifetimes. This process forms a layered composition within the star, much like an onion, with lighter elements fusing in the outer layers and heavier ones towards the core. This stratification is essential for the eventual supernova explosion, mixing elements and sending them out into the galaxy. Have you ever wondered about the role of magnetic fields in stars? These fields can be twisted and tangled by the star's rotation and convective motion. Particularly in more massive stars, these magnetic fields can influence the fusion process by affecting the distribution and flow of plasma in the star's interior. This, in turn, can lead to phenomena such as star spots, which are analogous to sunspots on our sun, but can be many times larger. Speaking of large phenomena, some stars undergo a process known as pulsation during certain stages of their life cycle. These pulsations are rhythmic expansions and contractions caused by changes in the star's fusion rate and structure. This pulsating behavior can lead to variations in brightness that are observable from Earth, giving astronomers clues about the internal processes of distant stars. Here's something that might surprise you. In certain binary star systems, fusion can lead to a phenomenon known as mass transfer. In these systems, one star can siphon material from its companion, triggering increased fusion rates. This can dramatically alter the life paths of both stars, sometimes resulting in explosive novae, a sudden brightening due to the rapid fusion of the transferred material. Can you imagine a star so powerful that its fusion processes can actually impact neighboring stars? In massive star clusters, the intense radiation pressure from a star's fusion can blow away surrounding gas, affecting the formation and evolution of other stars in the vicinity. This interplay of forces in stellar nurseries is essential for understanding the dynamics of star formation in galaxies. And here's a thought-provoking concept. The heaviest elements in the universe, such as gold and uranium, are not formed during regular fusion processes, but rather during the violent deaths of stars. When a supernova occurs, or when neutron stars collide, the extreme conditions allow for rapid neutron capture, a process known as the R process, creating these heavier elements that we find here on Earth. Reflecting on the nature of fusion, consider the idea of metallicity, which, in astronomical terms, refers to the abundance of elements heavier than helium in a star. This metallicity can influence the star's fusion processes and life cycle. Stars with higher metallicity tend to have more complex fusion pathways and can experience different evolutionary outcomes compared to low metallicity stars. Did you know that the concept of stellar winds is intricately linked to fusion? These are streams of charged particles driven away from a star's surface by its fusion energy. Stellar winds can significantly alter a star's mass over time and play a crucial role in shaping the interstellar medium, the vast space between stars filled with gas and dust. Here's something delightful. Fusion not only provides light and heat, but also creates neutrinos, nearly massless particles that zip through space at almost the speed of light. Billions of these particles pass through your body every second without you even noticing. They provide a unique window into the fusion processes occurring deep within stars, as they can escape the dense stellar interiors and reach Earth. Speaking of journeys across space, consider how fusion is at the heart of the cosmic distance ladder. The luminosity of certain types of stars, known as standard candles, can be used to measure astronomical distances. Understanding the fusion processes within these stars allows astronomers to calculate their intrinsic brightness, which is essential for mapping the scale of the universe. And let's not forget how fusion in stars provides an archive of cosmic history. By studying the light spectra of stars, we can determine their chemical composition and infer the processes that have occurred within them. This spectral fingerprinting offers insights into the history of element formation in the universe, from the earliest stars to present-day galaxies. As we continue this celestial exploration, it becomes apparent that fusion is not just a process confined to stars, but a cosmic symphony that echoes across the vast expanse of the universe, shaping everything we see and know. From the smallest particles to the largest galaxies, the dance of fusion connects us all in a universal tapestry of light and matter. Let me share something truly captivating with you. The fusion processes in stars don't just create elements, they also influence the very structure and evolution of the galaxies themselves. Did you know that the energy released by fusion in massive stars can drive powerful galactic winds? These winds can carry vast amounts of gas out of galaxies, which can suppress star formation and alter the galaxy's evolution over billions of years. It's a fascinating thought, isn't it? Here's another intriguing aspect. The fusion processes in stars are responsible for the varied colors we see in the night sky. Different stars exhibit different colors based on their surface temperatures, which are direct results of the fusion reactions occurring within them. For instance, the hottest stars, with temperatures reaching up to 50,000 degrees Kelvin, appear blue, while cooler stars, with temperatures around 3,000 degrees Kelvin, appear red. This colorful display is a beautiful visual manifestation of the fusion energy at work. Speaking of colors, did you know that fusion is also responsible for creating the elements that give planets their diverse characteristics and compositions? The iron core of Earth, the silicon in rocks, and the calcium in our bones all originated from the fusion processes in ancient stars. These stars, long since gone, have left behind a legacy of stardust that has coalesced into planets and even life itself. Isn't it amazing to think that we are, quite literally, made of star stuff? And here's something that might surprise you. The energy produced by fusion in stars is not simply a byproduct of their existence. It plays a crucial role in maintaining their stability. The outward pressure of the fusion-generated energy counteracts the inward pull of gravity, keeping the star from collapsing under its own weight. This delicate balance ensures that stars can shine steadily for billions of years, providing the light and warmth necessary for life to thrive on planets like Earth. Consider this. While we often think of stars as isolated entities, their fusion processes can have profound effects on their cosmic neighbors. For example, in some binary star systems, the fusion-driven stellar winds from one star can strip away the outer layers of its companion, altering both stars' evolutionary paths in a dramatic cosmic dance. Such interactions can lead to exotic objects like X-ray binaries and pulsars, which are some of the most energetic phenomena in the universe. Here's a thought-provoking fact. The fusion processes in stars not only generate energy, but also lead to the gradual evolution of the stars themselves. As a star consumes its hydrogen fuel, it transitions through various stages, from a main sequence star to a red giant and eventually to a white dwarf, neutron star, or black hole. Each stage is marked by different fusion reactions, creating new elements and releasing energy in unique ways. It's a testament to the dynamic and ever-changing nature of the cosmos. If you find that interesting, you'll be intrigued to learn about the role of fusion in the creation of planetary nebulae. When a star like our Sun reaches the end of its life, it sheds its outer layers, leaving behind a hot core. The ultraviolet radiation from this core ionizes the ejected material, creating a stunningly beautiful shell of glowing gas. These planetary nebulae serve as the final act of the fusion processes, a cosmic farewell that enriches the interstellar medium with new elements. Another fascinating aspect of fusion in stars is the concept of nucleosynthesis. This is the process by which new atomic nuclei are created from pre-existing nucleons, primarily through fusion reactions in stars. It's through nucleosynthesis that elements beyond hydrogen and helium are formed, building up the periodic table within the hearts of stars. Each generation of stars enriches the universe further, playing a pivotal role in the chemical evolution of galaxies. Have you ever imagined what it would be like if fusion in stars didn't occur? Without fusion, stars would not shine, and the universe would be a dark, cold place devoid of complex elements. The very processes that drive nuclear fusion are fundamental to the universe as we know it, providing the energy and building blocks for everything from simple molecules to complex life forms. Here's a curious thought. The study of fusion in stars has deepened our understanding of time itself. By observing the light from distant stars, which can take millions or even billions of years to reach us, astronomers can look back in time and study the universe's history. This cosmic archaeology reveals how stars and galaxies have changed over time, offering insights into the processes that have shaped the cosmos. Reflecting on the diverse roles fusion plays in stars, it's intriguing to consider the concept of stellar lifespan. While the lifespan of a star depends on its mass, with more massive stars burning through their fuel faster, fusion determines the stages a star will undergo throughout its life. This journey from birth to death, driven by the relentless power of fusion, is a saga of change and transformation on a cosmic scale. As we continue to ponder the profound impact of nuclear fusion in stars, let us remember that this process is not just a distant cosmic phenomenon, but an integral part of our own existence. From the light that warms our planet to the elements that constitute our physical bodies, fusion in stars is a reminder of our deep connection to the universe. Each star, with its unique fusion story, contributes to the grand symphony of the cosmos, a testament to the beauty and complexity of the universe we inhabit. Let's delve a little deeper into the marvels of nuclear fusion in stars. You might be intrigued to learn that the size of a star can dramatically influence the types of fusion reactions that occur within it. For instance, smaller stars, known as red dwarfs, sustain fusion in a more leisurely manner, burning their hydrogen fuel slowly over trillions of years. This slow burn means that red dwarfs are incredibly long-lived, and some might even outlast the universe as we currently understand it. Now think about this. While red dwarfs take their time, massive stars race through their fuel at an incredible pace. These colossal stars are able to initiate fusion of heavier elements like carbon, oxygen, and even iron in their cores. However, the fusion of iron is the endgame for these giants. Unlike lighter elements, iron fusion consumes energy rather than releasing it, leading to a precarious situation where the star can no longer support itself against gravitational collapse. This brings to mind the cataclysmic event known as a supernova, which is the explosive death throes of a massive star. During a supernova, the intense pressure and temperatures cause rapid fusion reactions that produce a cocktail of heavy elements, seeding the universe with materials that become part of new stars and planets. It's fascinating to think that gold, silver, and other precious metals were forged in the fiery crucible of a supernova. Here's a fun fact. The Sun, our very own star, is currently in a stable phase of its life, converting hydrogen into helium in its core. This process, known as hydrogen burning, releases energy that powers the Sun and provides light and warmth to our planet. However, in a few billion years, the Sun will exhaust its hydrogen supply and begin fusing helium. This will cause it to expand into a red giant, engulfing the inner planets and drastically altering the solar system. And, speaking of altering systems, did you know that the pressure at the core of a star like the Sun is about 200 billion times greater than the atmospheric pressure on Earth? This immense pressure is crucial for overcoming the electrostatic repulsion between positively charged nuclei, allowing fusion to occur. It's like a cosmic pressure cooker, where the conditions are just right for nuclear fusion to take place. On a related note, the energy produced in the core of a star doesn't immediately escape into space. In fact, it can take thousands to millions of years for energy created by fusion to travel from the core to the star's surface. This slow journey through the radiative and convective zones of the star ensures a steady and prolonged release of light and heat. Let's consider white dwarfs for a moment. These are the remnants of stars like our Sun that have shed their outer layers. Although fusion ceases in white dwarfs, the intense gravitational compression and the leftover heat from previous fusion processes keep them glowing faintly for billions of years. They're like cosmic embers, gradually cooling over time. Here's an intriguing aspect of fusion in stars. During their lifetimes, stars convert a staggering amount of mass into energy. According to Einstein's famous equation E squared A squared mc squared, a small amount of mass can be transformed into a huge amount of energy. Even the Sun loses about 4 million tons of mass every second as it fuses hydrogen into helium, a reminder of the sheer power of nuclear fusion. Did you ever wonder how astronomers study fusion in distant stars? One method involves analyzing the light emitted by stars, which contains spectral lines that reveal the presence of different elements and the processes occurring within the star. By examining these lines, scientists can infer details about the fusion reactions happening inside stars, like a cosmic fingerprint providing clues to stellar mysteries. Another captivating idea is the role of fusion in creating neutron stars. When a massive star explodes in a supernova, the core that remains can collapse into a neutron star. These incredibly dense objects are composed almost entirely of neutrons, with a single teaspoon of neutron star material weighing billions of tons. The fusion processes that preceded their formation set the stage for these exotic remnants. It's also worth noting the phenomenon of stellar pulsations driven by fusion in the cores of certain stars. These pulsations cause stars to expand and contract in a rhythmic fashion, emitting regular pulses of light. Cepheid variables, a type of pulsating star, have been crucial in measuring cosmic distances and helping us map the universe. Lastly, let's touch upon the concept of helium flash, an explosive event that occurs in the cores of low-mass stars as they begin fusing helium. This sudden burst of energy marks a new phase in the star's life, leading to changes in its structure and luminosity. It's a dramatic turning point, showcasing the dynamic nature of fusion and its transformative impact on stars. As you ponder these fascinating insights into nuclear fusion, consider how each fact adds a layer of complexity to our understanding of stars. From the slow-burning red dwarfs to the explosive demise of massive stars, fusion plays a central role in the life cycle of stars, shaping the universe and everything within it. The more we learn about this cosmic process, the more we appreciate the intricate and wondrous fabric of the cosmos. Let me share something interesting. Not all stars are born in solitude. Many stars are part of binary or multiple star systems, where two or more stars orbit each other. In these systems, nuclear fusion can lead to fascinating interactions. For instance, a white dwarf in a binary system can pull matter from its companion star. This accreted matter can ignite in a runaway fusion reaction, resulting in a nova, a spectacular outburst of light and energy visible across vast distances. And speaking of light, did you know that the color of a star is directly related to its surface temperature, which in turn is influenced by the fusion processes in its core? Blue stars are much hotter and more massive, with higher fusion rates, while red stars are cooler and less massive, burning their fuel more slowly. This color-temperature relationship is a key tool for astronomers when classifying stars and understanding their life stages. Here's another intriguing thought. The fusion reactions in stars are responsible for creating all elements heavier than hydrogen and helium. This process, known as nuclear synthesis, occurs over millions to billions of years and is a cornerstone of cosmic evolution. Without these elements, planets and life as we know it would not exist. It's humbling to realize that the building blocks of life were forged in the hearts of stars. Can you imagine the scale of energy required for these processes? The core of a star where fusion occurs reaches temperatures of millions of degrees. This extreme heat is necessary to overcome the electrostatic forces that repel atomic nuclei from each other. Without such incredible temperatures, the fusion reactions that power stars and produce elements could not occur. On a related note, the various fusion processes in stars are not uniform but change over time. In its earlier stages, a star primarily fuses hydrogen into helium, but as it ages, it can begin fusing heavier elements like carbon and oxygen. These changes in fusion pathways alter the star's size, brightness, and lifespan, painting a dynamic picture of stellar evolution. Here's a fascinating fact. While our Sun is in a stable hydrogen-burning phase, there are stars much older that have entered more advanced fusion stages. These stars, known as red giants and supergiants, have exhausted their hydrogen and are now fusing heavier elements. Their expanded outer layers and increased luminosity are a testament to the complex and varied life cycles of stars. And did you know that fusion processes are not limited to massive stars? Even small stars, known as red dwarfs, undergo fusion, albeit at a much slower rate. These stars can burn their hydrogen steadily for trillions of years, far outlasting larger stars. This longevity makes red dwarfs some of the most common and enduring stars in our galaxy. Speaking of longevity, The end stages of a star's life are equally fascinating. After a star has exhausted its nuclear fuel, its core can become a white dwarf, a neutron star, or even a black hole, depending on its initial mass. Each of these outcomes is the result of different fusion histories and represents a distinct chapter in the story of the universe. Let me tell you about something called triple alpha process, a fusion reaction that occurs in the cores of older stars. When a star begins fusing helium, 3 helium nuclei can combine to form carbon. This process is crucial for producing carbon, an element essential for life. Without the triple alpha process, the universe would be a very different place indeed. Another surprising aspect of stellar fusion is the role of metallicity, or the abundance of elements heavier than helium in a star. Stars with higher metallicity tend to have more complex fusion processes and may evolve differently than their metal-poor counterparts. This relationship between metallicity and fusion adds another layer of diversity to the stellar landscape. Here's something to ponder. The fusion reactions in stars are not only crucial for the stars themselves, but also have a profound impact on their surrounding environments. The energy and particles released by fusion can create stellar winds and shock waves that shape the formation of new stars and planetary systems. This feedback loop ensures that the life cycle of stars is interconnected with the broader cosmos. And speaking of interconnectedness, the fusion of elements in stars is intricately linked to the cosmic timescale. The rate at which stars form, evolve, and die influences the chemical composition of galaxies and the universe as a whole. Each generation of stars contributes to the richness of the interstellar medium, paving the way for future stellar generations. Lastly, consider the fact that the principles of nuclear fusion in stars are not just theoretical, but have practical applications here on Earth. Scientists are working to harness the power of fusion for clean, sustainable energy, inspired by the processes that fuel the stars. The pursuit of controlled fusion is a testament to our desire to understand and emulate the natural wonders of the universe. As we explore these surprising facets of nuclear fusion in stars, we're reminded of the intricate ballet of forces and reactions that define our cosmos. Each fact unveils another layer of complexity and wonder, inviting us to appreciate the universe as a vast and interconnected tapestry. With every discovery, we come closer to understanding the profound and beautiful mechanics that govern the stars above us. Let me share something interesting with you. In the early universe, shortly after the Big Bang, hydrogen and helium were the predominant elements, with almost no heavier elements present. It was the process of nuclear fusion in the first generation of stars that began the cosmic alchemy, transforming these light elements into the heavier ones that form the building blocks of matter we see today. This reminds us how essential fusion is to the very structure of the universe. Here's a fascinating fact. Not all stars have a happy ending. Some massive stars, after fusing elements up to iron, meet a dramatic fate as supernovae. These explosive events scatter the elements forged in the star's core into space, enriching the interstellar medium with the ingredients for new stars and planets. Can you imagine the power of such an explosion, briefly outshining an entire galaxy? Speaking of explosions, there's something intriguing about the role of pressure in a star's core. The immense gravitational forces of a star compress its core to such a degree that temperatures soar high enough for fusion to occur. This balance between gravitational pressure and the outward pressure from fusion reactions is what keeps a star stable. Without this equilibrium, stars would either collapse under their own gravity or explode outwards. And did you know that fusion in stars isn't always a smooth, continuous process? In some stars, particularly those undergoing helium fusion, the reactions can occur in bursts known as helium flashes. These sudden and intense bouts of fusion can dramatically alter the star's luminosity and appearance. It's as if the star is catching a breath before continuing its cosmic journey. Here's something curious. While we often think of stars as solitary entities, many stars are part of binary systems. In such systems, the fusion processes of one star can significantly influence the evolution of its companion. Material can be transferred from one star to another, potentially leading to the dramatic ignition of fusion processes in the receiving star's outer layers, sometimes resulting in a nova. It's also worth noting that not all fusion processes are the same. For instance, in very massive stars, a process known as the CNO cycle takes over the fusion of hydrogen into helium. This cycle involves carbon, nitrogen, and oxygen as catalysts, making it different from the simpler proton-proton chain reaction that occurs in less massive stars like our Sun. The CNO cycle is highly temperature dependent, and it's fascinating how these different pathways emphasize the diversity of stellar processes. Here's a surprising thought. The smallest stars capable of sustaining fusion, known as brown dwarfs, exist in a delicate balance on the threshold of fusion. They are sometimes called failed stars because they are not massive enough to sustain the continuous fusion of hydrogen into helium. However, they can briefly fuse deuterium, a rare isotope of hydrogen, providing a glimpse of the power just out of their reach. Connecting back to our own solar neighborhood, did you know that the Sun's fusion processes have influenced not only the solar system's formation, but also its weather? The solar wind, a stream of charged particles released from the Sun's outer layers, is a direct result of nuclear fusion. This solar wind shapes planetary atmospheres and can even affect Earth's magnetic field, leading to phenomena like auroras. Have you ever wondered what makes stars twinkle? Interestingly, while the twinkling effect is primarily due to Earth's atmosphere, the light emitted from stars is a direct product of fusion. The steady fusion reactions within a star's core release energy that travels across millions of kilometers, unfazed, until it encounters our atmosphere. This light, flickering from the distant cosmos, is a testament to the ancient fusion processes that continue to illuminate our night sky. On a broader cosmic scale, nuclear fusion doesn't just create elements and energy, it also plays a role in the formation of new stars. The remnants of dead stars, enriched with heavy elements produced by fusion, can collapse under gravity to form new stellar nurseries. These nurseries are the cradles where new stars are born, continuing the cycle of stellar evolution. Now, let's consider the fascinating symmetry in fusion processes. The Sun and other stars burn hydrogen in their cores through fusion, but when hydrogen is a fuel on Earth, such as in hydrogen fuel cells, it provides energy through a chemical reaction. This elegant parallel highlights how fusion, whether in the heart of a star or in future energy technologies on Earth, remains central to energy production. Here's another thought. The fusion reactions in stars set the stage for the complex chemistry that leads to life. The carbon, nitrogen, and oxygen cycles in stars create a rich tapestry of elements, some of which are crucial for the biochemistry of life as we know it. The implications are profound, suggesting that life across the universe, if it exists, might share a common ancestry in the stars. Finally, let's marvel at the sheer timescales of fusion in stars. While human history spans mere thousands of years, stars like red dwarfs can persist for trillions, slowly burning their fuel at a sedate pace. This immense longevity ensures that fusion, as a cosmic process, is a nearly eternal feature of the universe, providing stability and continuity amid the ever-changing cosmos. As you drift into sleep, remember that the starlight that bathes us is a constant reminder of these ancient and ongoing fusion processes, connecting us to the universe's past, present, and future. As we drift deeper into the mysteries of nuclear fusion in stars, let's ponder the incredible densities within a star's core. Did you know that the core of a star like our Sun is unimaginably dense, with the pressure reaching over 200 billion times that of Earth's atmosphere? This immense pressure is what enables the fusion of hydrogen into helium, a process that has been ongoing for billions of years. It's awe-inspiring to think that such extreme conditions are commonplace in the universe. Here's an intriguing insight. The fusion process in stars is remarkably efficient. In the Sun, for every second that passes, around 600 million tons of hydrogen are converted into helium. Yet, the Sun will continue to shine for another 5 billion years. This efficiency ensures that stars are long-lived, stable sources of light and energy, providing the perfect conditions for life to evolve. Speaking of longevity, have you ever considered the fate of massive stars? While smaller stars burn steadily and live longer, massive stars have a different destiny. They burn through their fuel quickly, leading to a spectacular finale. When their fusion processes can no longer balance gravity, these stars explode as supernovae. The remnants of these explosions, such as neutron stars or black holes, are among the most extreme objects in the universe. It's fascinating to think that the end of a star's life can bring about such dramatic cosmic events. Another captivating thought: the very first stars in the universe, known as population 3 stars, were primarily composed of hydrogen and helium, with almost no heavier elements. These ancient stars set the stage for the synthesis of heavier elements through their fusion processes. When they reached the end of their lifespans, they enriched the cosmos with elements that would eventually form planets and life. It's a humbling reminder of our deep connection to the cosmos. A surprising fact about stars is the role of magnetic fields. Did you know that stars can have incredibly strong magnetic fields? These fields are generated by the movement of charged particles within the star, a direct result of fusion processes. Such magnetic fields can influence stellar winds and even affect the star's rotation, showcasing the intricate interplay of forces within a star. Let's turn our attention to the concept of metallicity in stars. In astronomy, metals refer to elements heavier than hydrogen and helium. A star's metallicity can tell us much about its history and the conditions in which it formed. Stars with higher metallicity are often younger and have formed in regions enriched by previous generations of stars. This fascinating detail helps astronomers trace the evolution of galaxies and star systems. These stars undergo changes in brightness due to variations in their fusion processes. One famous example is the Cepheid variable stars, which pulsate in a predictable pattern. These pulsations occur because of periodic expansions and contractions in the star's outer layers, driven by fusion dynamics. The regularity of their brightness makes them valuable tools for measuring cosmic distances. An especially captivating phenomenon is the fusion happening in white dwarfs. Although these stellar remnants no longer sustain fusion in their cores, they can still experience explosions known as novae. This occurs when a white dwarf in a binary system accretes material from its companion star. Once enough hydrogen accumulates on the white dwarf's surface, fusion can ignite, leading to a dramatic outburst of light. It's remarkable to consider the variety of fusion reactions that can occur in stars. For instance, in the final stages of a massive star's life, silicon fusion takes place. This process results in the production of iron, the heaviest element formed in a star's core before it goes supernova. This transition from silicon to iron signifies the end of a star's energy-producing potential, as iron fusion does not release energy. Speaking of energy, the concept of the neutrino cooling process in stars is a lesser-known but intriguing aspect of fusion. Neutrinos, nearly massless particles produced during fusion, can escape from the core of a star, carrying away energy. This process becomes significant in the later stages of a star's life, affecting its evolution and eventual demise. It's astonishing to think that such tiny particles can have a profound impact on stellar life cycles. Another delightful discovery is the role of fusion in the creation of cosmic dust. When stars shed their outer layers or explode in supernovae, the elements forged through fusion are dispersed into space. Over time, these elements coalesce to form dust grains, which become the building blocks of planets, moons, and even life itself. This cosmic recycling highlights the interconnectedness of all matter in the universe. The diversity of fusion processes doesn't stop there. In certain stars, fusion can produce lithium, a rare element in the universe. However, the lithium created in stars is often destroyed later in the star's life. This makes the study of lithium in stars a crucial tool for understanding stellar evolution and the history of galaxies. Finally, let's appreciate the role of fusion in shaping the universe's large-scale structure. The energy released by fusion in stars contributes to the dynamics of galaxies and galaxy clusters. It's fascinating to consider how the processes within individual stars can influence the behavior of entire galaxies, driving the cosmic dance of matter and energy. As you ponder these surprising facts, let them guide your thoughts towards the vastness and wonder of the universe. The story of nuclear fusion in stars is one of constant creation, transformation, and connection, echoing throughout time and space. As you drift into a peaceful slumber, let the knowledge that we are all made of stardust bring you comfort and inspiration, connecting you to the universe's ancient and ongoing tale. As you continue to explore the fascinating world of nuclear fusion in stars, let me share something interesting: the concept of stellar nucleosynthesis. This incredible process is responsible for creating most of the elements we find in the universe today. Just imagine the very carbon in your body, the calcium in your bones, and the oxygen you breathe were all forged in the hearts of stars through nuclear fusion. It's a testament to the remarkable capabilities of these celestial bodies, endlessly shaping and reshaping the cosmos. Speaking of reshaping, did you know that the different layers within a star play unique roles in the fusion process? In massive stars, there are distinct zones where different fusion reactions occur, each producing various elements. This layered structure resembles an onion, with the outer layers still burning lighter elements, while the core processes heavier ones. The intricate layering is a complex ballet of energy production that sustains the star's life. And here's something truly remarkable. The fusion process within stars doesn't just produce light and heat, it also generates neutrinos, those elusive particles we touched on earlier. These neutrinos travel through space at nearly the speed of light, barely interacting with matter. The sheer number of neutrinos produced by the sun alone is mind-boggling, with trillions passing through your body every second without you ever feeling a thing. Let me tell you about an unexpected aspect of fusion. The energy output of stars is incredibly stable, thanks to a natural balancing act. Stars achieve a state known as hydrostatic equilibrium, where the outward pressure from fusion balances the inward pull of gravity, maintaining a delicate harmony. This balance ensures that stars can shine steadily for billions of years, providing life-sustaining light and warmth to any planets orbiting them. Have you ever wondered about the role of fusion in the birth of stars? When massive clouds of gas and dust collapse under gravity, the heat generated from this collapse ignites nuclear fusion in the core, heralding the birth of a new star. This process not only marks the beginning of a star's life, but also helps to clear away surrounding material, shaping the emerging solar system. The birth of a star is a truly dynamic event, punctuated by the brilliant ignition of fusion. Here's a fascinating fact. Not all stars are created equal, and their initial mass determines their entire life cycle. For instance, low-mass stars like red dwarfs can sustain fusion for trillions of years, thanks to their efficient use of fuel. In contrast, the most massive stars burn out quickly, living fast and ending their lives in spectacular supernova explosions. The diversity of stellar lifetimes is a direct result of the fusion processes at play. Speaking of diversity, let's consider the intriguing concept of stellar convection. In certain stars, hot plasma rises towards the surface, cools down, and then sinks back to the core in a continuous cycle. This convection process not only transports energy, but also mixes the star's interior, bringing fresh hydrogen into the core to fuel further fusion. Convection is a vital mechanism that prolongs a star's life by making the most of its available resources. Another surprising aspect of fusion is its role in the cosmic alchemy of star formation. In the densest regions of galaxies, where gas and dust clouds are abundant, the gravitational pull can trigger the formation of multiple stars in close proximity. These new stars may engage in gravitational interactions, sometimes forming binary or even triple star systems. The gravitational dance of these systems is a beautiful consequence of the widespread influence of fusion. And here's a delightful twist. The very energy that sustains stars can also lead to their demise. In massive stars, once iron accumulates in the core, fusion can no longer produce energy, leading to a catastrophic collapse and a subsequent supernova explosion. This dramatic end is not the final word, however, as the elements scattered by the explosion become seeds for new stars and planets, continuing the cosmic cycle of creation and destruction. Now, let's explore a lesser-known but captivating fact. The temperature at which fusion occurs within stars is astonishingly high. In the Sun's core, where hydrogen nuclei fuse into helium, temperatures reach around 15 million degrees Celsius. This intense heat is necessary to overcome the repulsive forces between atomic nuclei and allow fusion to proceed. The star's core is a cauldron of unimaginable energy, driving the fusion that powers its brilliance. Speaking of brilliance, did you know that the energy produced by fusion in stars is ultimately responsible for the colors we see in the night sky? The different temperatures and compositions of stars result in a variety of hues, from the cool red of aging stars to the hot blue of young, massive ones. This dazzling array of colors is a direct consequence of the fusion processes sustaining these distant suns. Finally, consider the role of fusion in the grand tapestry of the universe. The energy released by fusion in countless stars contributes to the cosmic web, the large-scale structure that binds galaxies together. This network of matter and energy is a testament to the far-reaching impact of fusion, echoing throughout the cosmos and shaping the universe as we know it. As you reflect on these surprising facts, let them inspire a sense of wonder and connection to the stars above. Each fact is a reminder of the intricate, dynamic processes that fuel the universe and our place within it. As you drift into a peaceful slumber, remember that the same forces that illuminate the night sky are at work within you, a testament to the incredible journey of stardust through time and space. Here's a delightful tidbit to ponder. The fusion process in stars is responsible for creating most of the elements found in the universe. Elements like carbon, oxygen, and nitrogen are forged in the hearts of stars through a process known as nucleosynthesis. As stars evolve, they create heavier elements by fusing lighter ones, enriching the cosmos with the building blocks of life. Without fusion, the universe would be a far simpler place, devoid of the diverse elements that make up planets and life as we know it. Speaking of elements, did you know that the life cycle of a star determines the kinds of elements it can produce? In the later stages of evolution, massive stars can reach temperatures high enough to fuse elements like silicon and magnesium. This process continues until iron is produced, beyond which fusion ceases to release energy, as iron absorbs more energy than it emits. This fascinating transformation illustrates the limits and powers of nuclear fusion at work within stars. Let me share something intriguing. Stars not only create elements, but also play a vital role in recycling them throughout the galaxy. When massive stars end their lives in supernova explosions, they scatter these newly formed elements across vast distances. This cosmic redistribution enriches interstellar clouds with heavy elements, contributing to the formation of new stars and planetary systems. It's a beautiful cycle of birth, death, and rebirth, driven by the relentless energy of fusion. Can you imagine how stars manage to shine with such brightness for so long? It turns out that the efficiency of fusion reactions plays a crucial role in a star's longevity. For instance, the Sun converts over 4 million tons of matter into energy every second, yet it utilizes only a fraction of its hydrogen fuel. This remarkable efficiency ensures that stars like the Sun have stable lifespans lasting billions of years, providing consistent light and warmth to their orbiting planets. Here's a curious fact. The core of a star is often too dense and hot for photons or light particles. Instead, it can take thousands of years for energy generated through fusion to make its way from the core to the surface. During this journey, energy is transferred through countless interactions and collisions, slowly diffusing outward. This slow travel time keeps stars stable, allowing them to radiate energy steadily over vast stretches of time. As you consider these facts, think about the role of fusion in stellar evolution. Stars spend the majority of their lifetimes in a phase known as the main sequence, where hydrogen fusion occurs in their cores. This stage is marked by stability and balance, yet eventually, stars exhaust their hydrogen supply, transitioning into later stages of fusion. Depending on their mass, stars expand into red giants or supergiants, continuing to fuse heavier elements in their cores. Speaking of transitions, let me tell you about the fascinating phenomenon of planetary nebulae. When medium-sized stars like the Sun exhaust their nuclear fuel, they shed their outer layers, creating breathtaking shells of gas and dust. The core, now exposed, becomes a white dwarf. The colorful, glowing nebulae left behind are lit by the ultraviolet radiation from the core, offering a vivid display of the remnants of fusion's powerful influence. And here's an astonishing concept. In the densest regions of our galaxy, stellar nurseries house the raw materials for new stars. Within these nurseries, countless stars are born, each igniting fusion at its core. These regions are often cloaked in thick dust, yet they are bustling with activity, as gravity pulls material together to form new stars. The interplay of fusion and gravity within these nurseries fosters the growth of the next generation of stars. It's captivating to think about the extraordinary end of massive stars, those that are more than 8 times the mass of the Sun. These stars ultimately collapse under their own gravity, triggering a supernova explosion. This cataclysmic event is so luminous that it can briefly outshine an entire galaxy. The supernova enriches the surrounding space with heavy elements, demonstrating fusion's role in cosmic enrichment. Consider for a moment the final remnants of a supernova: neutron stars and black holes. Neutron stars are incredibly dense, with matter so tightly packed that a sugar cube-sized amount would weigh as much as a mountain. Black holes, on the other hand, are regions of space-time where gravity is so strong that nothing, not even light, can escape. These remnants are a testament to the extreme conditions and outcomes of stellar fusion. Here's something to ponder as you drift off. The interplay of fusion and gravity doesn't just shape individual stars, but it also influences galaxies as a whole. The energy released from fusion contributes to the balance of forces within galaxies, affecting their structure and evolution. This cosmic choreography highlights the interconnectedness of all things in the universe, with fusion serving as a key player in the grand dance of life and matter. As you reflect on these surprising facts, let them fill you with awe and wonder at the vastness of the universe and the delicate balance that allows stars to shine. The fusion within stars is not just a process of immense power. It is a source of beauty and life, connecting us to the cosmos in ways both profound and serene. As you gently close your eyes, remember that the story of fusion is the story of the universe itself, a testament to the enduring power of creation and transformation.